design a closed eigenvalues, you can make sure that your closed eigenvalue, that for that many eigenvalues, that the final this matrix, and this is nothing but your eigenvectors. So that your eigenvector 1, your eigenvector 2, and your eigenvector 3, and so on. And this eigenvector means those eigenvectors as orthogonal as possible. Now, if this is orthogonal to that, if that orthogonal to that, then inverse is good. That means they are very independent. This independent, that independent. If this depends on that, then you get an inverse. Right? So that is that is some of the remarks you need to understand when you use these techniques. Okay. Now, hopefully we can have time to look at an example. Closed eigenvectors. That's my closed eigenvectors. These are eigenvectors. What is my desired eigenvector? I can have a desired eigenvectors. The desired eigenvector, desired eigenvectors doesn't mean you can get that, but you can get as close as possible to my desired closed eigenvectors. For example, like this, right? Let's see. That's my head. Sorry, that's my head. Okay. I think this is also head, right? Yeah. Then this is head. Okay. So this is my desired eigenvectors and my desired eigenvectors. So I have a desired eigenvector and desired eigenvectors. Now, hopefully I can get my desired eigenvector. However, now if you cannot get a desired eigenvectors, then I want to have my CK such that I can as close as possible to my desired vectors. All right. So that this is something we use in our design, and I just share with you about this. What happened to this guy, this software, All right. Let me explain to you a little bit more. If you look at these equations, if you look at that equation here, that is, I want to have this vector, my vector. She might have freedoms. She might have freedoms. That is my. We know that the phi k is equal to V0k and ck. And that V0k, I'm going to divide it to be two pieces, one bar, one 0k head, ck. All right, and this is, if we're giving this, then that's my actual, I call actual phi k. And assume, say, I have a desire one. I have desire. So I have, say, mine, I have desire free k, that's desired, I call d free k. My desired one equal to this free k bar dk and free bar free head dk. So this is my desire. Why I want to design like this? Because I wanted this guy, desired one, as orthogonal, as independent as possible for k equal to 1 to n. My desired one means my free one, desired 1, and free desired 2, and free desired n. That matrix is, I hope this my design is all very independent so that my inverse is good, so that I can invert it. That's the tricks here. All right. Now, but this design one doesn't mean I can get it. So what is the best to see so that this k is approached to my dk? That's the case. I want to choose a ck such that my free k approach to my dk. Okay. Now, the problem here is this, because free k, this v0k is not square. If this v0k is square, then I can always get my desire. Right? If I have a v0k that's a square matrix, then I can get any vector I want with a ck. Right? Now, how can I get that? So what is the best to get that? Assume that, say, free dk, I want to, this can be equal to v0k to ck. Can I get that? The answer is no. You cannot get equal. Unless the equal is not possible. Unless v0k is a square matrix and invertible. Invertible. Right? If that is not square matrix, if this is not square matrix, then you cannot get exact free d0k. The only way you can get that is that to have a, we call least square solutions. Now, least square solution means ck. So that means that ck is equal to v0k pseudo inverse and then free dk. So that's the ck I can get. If this is square, then that's mean inverse. Then I can get ck exact. But if not, then that means I can get this ck if I sub in this key ck into my system. That means my real k will be equal to v0k pseudo inverse times v0k the free that means my real 0 free k v0k pseudo inverse free dk. Right? That's my real one. That's my real one. You understand about this? No? Alright, well, anyway, I explain this later because this is already over time. I'm gonna give you example so that you can understand better. But don't forget to come next week. That's our midterm. Again, midterm is open book, open notes. Just can bring your computer here. You can have your small calculator if you want. All right. Is that good? All right. And we have about 2.5 hours exam. Typically, we have about 4 to 5 problems for you to solve. If you listen carefully about all my notes here, you won't have any problem. Okay, see you next week.